All right. Hello, everybody. Good evening and welcome to the South Carolina State Museum's Boeing Observatory live stream. My name is Liz Klimek. I'm actually the planetarium manager, and this is Mr. Matthew, our observatory manager. Laura is out this evening, but she will be back next Saturday. All right, so before I get started, thank you everybody for joining us tonight. If you have a question at any point in time, be sure to put that in the chat and we'll make note of it and try to answer as many of your questions as possible. We want to give a quick shout out to Boeing. Thank you for sponsoring the observatory and allowing us to do all the wonderful things that we do. And also thank you so much to our members for your continued support. It's very, very much appreciated. All right, well, Matthew, what do we have for this evening?
Oh, we've got some really cool stuff this evening. I'm actually really excited about this episode tonight because tonight we're going to talk about giant telescopes around the world. And actually, we're going to focus on two places, the United States and then down in Chile, Chile is where a lot of really big telescopes are being built right now. And one of the things that we want you all to take away from this is that these giant telescopes that are being built, and these are telescopes that are much larger, by the way, than the Hubble Space Telescope and also the James Webb Space Telescope, and they're being built here on Earth. But one thing I want you all to take away is that these are telescopes that are under construction now. Astronomers aren't just talking about this. These are not just ideas and dreams. These telescopes are actually being built on mountaintops. Their mirrors are being made. We're actually going to show you how the mirrors for these telescopes are made. They're made in a mirror lab under the football stadium at the University of Arizona in Tucson. And there's a personal connection there because I am a University of Arizona graduate, and I have been in the mirror lab a whole bunch of times as part of an astronomy camp I used to teach for. So we'll have a lot of fun showing you this really awesome process that is used to make these mirrors. Before we get to that, though, I just want to go ahead and pop up a view of the moon. We do have a really nice view of the moon today, so I'm going to get that going for you here. I hope. What happened to my moon view? Just a second. This is what happens. I have so many silly windows open right now that it's like, where is everything? Okay, let's see. I might need to get out of that.
Well, while you're doing that, I do want to mention, because I forgot to mention it at the beginning of the stream, there is a 20-second delay between us and the Facebook Live here. Oh, thanks, Sarah Catherine. We do have a question about AstroKid stamps. Actually, if you want to email us, or actually, Matthew, is it better if they email you about the AstroKid stamps or just directly membership?
Direct to membership, and then they should be able to get it to us here. All right.
Yeah, if you have a question about AstroKid stamps, because I know the observatory and the planetarium is currently closed now until at least the end of February, go ahead and email our membership, and you can find that email address on our website at scmuseum.org, and we can get you taken care of there.
Okay, I now have a view of the moon. Sorry, I have got so many windows going. This is probably going to be a theme for me having to go find things and just run screen share for. So here we go. Let's get ourselves a nice view of the moon. So right now we're looking at a very small area of the moon. So we're actually, again, using that really small telescope that rides alongside the big Clark. And this telescope and camera combination does not give us that big an area of the sky. So we only can see a small part of the moon. So right now we're looking at this nice crater right here, and then you've got these rays that are coming off the crater all across here. These rays were probably formed, or actually they were formed, when whatever hit the moon there smacked into the moon, and then it scattered a whole lot of stuff off in every direction, like, ugh. And that's how we got all those rays. So when we have large craters on the moon, we tend to see those ray structures.
So what part of the moon are we looking at? Are we looking towards the northern half, the southern half? Can you give folks a rough idea of where we're pointed at on the moon right now?
Right now we're pointed at near what's called the terminator. So that light dark line is where we're looking, which is actually why the image kind of looks dark. We're in an area of the moon where the shadows are quite long. And so because the sunlight here is not terribly direct. So what I think we're going to do at the end, if we have time, is show the moon again, and we're going to drive the telescope around so you can feel like you're an astronaut floating in space over the
Driving around the moon. One of my favorite parts of Apollo history is the fact that there are moon buggies. They had moon buggies, Apollo 15, 16, and 17, and it's always my dream to just drive a buggy across the moon. So get to drive. And just to clarify, the terminator is the dividing line between the daylit side of the moon and the nighttime side of the moon. So when you're right on that edge there, as Matthew said, you get some nice features there that you can see.
I sometimes will joke the Terminator, that sounds kind of violent, doesn't it? Like you're going to
It does. Yeah, it's doesn't really help that there's a movie called that, but it's just the dividing line between the daytime and the nighttime side. So
yeah. Yeah, and then again, you can see this sort of wiggling right here. Again, this is not the moon doing that. That's our own atmosphere making that sort of wiggling motion.
We do have a question here. When did the planet that formed the moon crash into Earth, and what was its name?
Oh, what was its name? Was it Vera? What are you remembering?
It did give a name to that body, and I don't remember what it was called. It wasn't technically a planet. I guess it was a big debris chunk, I guess, back when the solar system was young and a lot of stuff was flying around.
Yeah, so it was really big, potentially about the size of Mars.
The size of Mars, not Mars itself. That's a very important, very important distinction.
Chunk of space junk the size of Mars hit the Earth way back when the solar system was first forming and the Earth was first forming, and made the moon, or knocked a whole bunch of stuff off into space, and that's how we got the moon.
Okay. All right, and if you're just tuning in, if you have any questions about what we're looking at or what we're discussing, feel free to put them in the chat, and I will do my best to keep monitoring that. All right, anything else you want to say about what we're looking at here, Matthew?
I think we're gonna go ahead and move away from the moon here, because I'm gonna try to make sure we have some time to look at it right towards the end, and then I'm going to get this is going to take me a minute with all these booming windows up. Too many windows! Let's see here, there's what I want. And now we are going to start our epic telescope journey. And I think the best place to start our epic telescope journey is right here in Columbia, South Carolina, at the South Carolina State Museum, because right behind me is a telescope. And if you've been here, you may have looked through our telescope. This is our 1926 Alvin Clark refractor. So we're going to be talking about telescopes that are much, much, much larger. This telescope behind me, the one we have here at the museum, has a lens that's about 12 inches across. We're going to be talking about telescopes that have mirrors. So modern research telescopes use mirrors instead of lenses. We're going to be talking about telescopes that have mirrors that are like 8 meters across. And we're going to be talking about some telescopes that have a whole bunch of mirrors that may combine to make an even bigger telescope. So really...
So first of all, why would you want to make a telescope bigger in the first place? Why isn't the Clark just big enough?
So astronomers are the greediest people on the planet for light. That's actually something you're going to see here. Astronomers will stop at nothing to build a telescope that will gather more light, because when you can gather more light, you can see further into space and you can see fainter things. And this is how you can learn about things like, well, how did the first galaxy form? What was the universe like just after the Big Bang when the first stars were forming? And then the telescopes that we're going to show you tonight, these are telescopes that might be involved in things like actually figuring out what's inside the atmosphere of a planet around another star. And if we can figure out what's in the atmosphere of a planet around another star, we might be able to figure out if there's life on that planet, because life gives off certain gases that you would expect to find in the atmosphere. So that's why astronomers are going to these huge lengths to build these giant telescopes, because there are these big burning questions that we want to answer. And astronomers are greedy for light. So have we generated any questions before we kind of get started?
There is a comment that Thea was indeed the body that crashed into Earth. Thank you, Debbie Gilbert. I could not remember the name, but isn't that what you said, Matthew? Thea?
I think I said Vera or something.
Vera.
Like that.
Oh, you said Vera. Okay. Yeah, Thea. Okay. Thanks, Debbie. All right.
All right.
And
we started our trip here in Columbia, South Carolina. And now we're going to get on a plane and we're going to fly across the country to Tucson, Arizona. Again, I went to the University of Arizona. I was there for about 8 years doing my graduate work. I taught for an astronomy camp there. I've been to a bunch of the observatories there. So there's kind of a personal connection, and that's one of the reasons I'm kind of excited about giving this presentation. We're going to go to Tucson, Arizona, which is a place where there are a lot of telescopes on mountaintops around the city. And we're going to take a look at one of them to get ourselves started. Here we go. Let me make my screen full-sized here.
all right, while you're doing that, I'm going to say hi, Judy, Aiden, and Nicholas. Thanks for joining us.
All right, so one thing about this is that we are going to kind of get off and talking about a bunch of slides. We're going to try to make this as interactive as possible, but please do not hesitate to stop us with questions and ask questions as we go through this. So we've taken our plane flight to Tucson, Arizona, and we're now on a mountaintop east of Tucson called Mount Graham. Mount Graham is this about 10,000 foot mountain. And on Mount Graham are several telescopes, including this one called the Large Binocular Telescope. Now, one of the things about astronomers is they tend to come up with really, really creative names for telescopes, like Large Binocular Telescope, Very Large Telescope, Telescope, Multiple Mirror Telescope. Can you come up with a more creative name for your telescope?
My favorite is Overwhelmingly Large Telescope.
Yes.
Overwhelmingly, extremely large telescope.
How about the Stupidly Immense Telescope? The SIT. So yeah, you're going to notice that astronomers don't have a lot of creativity when they come up with telescope names. This telescope, the Large Binocular Telescope, is one of the first telescopes in this generation of giant telescopes. So for a while, it seemed like the sizes of telescopes were stuck. We had telescopes that were like 4 meters across. So when we talk about big telescopes, we talk about the size of them in meters. So Hubble is a 2.5 meter telescope, for example. But we had telescopes that were like 4 meters across and then 5 meters or 200 inches across. That's the telescope out on Palomar in California. And telescope building kind of got stuck because we didn't really have a way to make their mirrors larger without making the structure that supports the telescope so huge that, number one, it'd be way too expensive to build, and number two, the thing would be really, really darn heavy. So we're going to show you kind of how astronomers do this, but first we're going to take you on a tour of some of these telescopes.
Oh, someone suggested the Big Eyeball Telescope.
I know, this telescope does look like 2 big googly eyes.
It does. It does. All I see is a face. That was the first thing I saw when I looked at this picture. Looks like a face with I just want to draw a little smiley face underneath.
We'll just ask this question to everybody out in the audience. Why do you think we would build a telescope with 2 mirrors?
2 versus 1. So if you think you know why we would build a telescope with 2 mirrors instead of just 1 single mirror, go ahead and type your ideas in the chat or any questions. So I'm not seeing anything yet. Let's see, many people need books. Need to think about it. Why would we want 2 mirrors instead of 1? Why not kind of a cyclops looking thing instead of these 2 googly eye looking things?
Yeah. Yeah.
I don't know. Right, instead of 1 big one. So yeah, so why would we have 2 mirrors like we have with the LBT here versus 1? So any ideas out there in Facebook land about why we would do that instead of just make 1 big mirror? How big were these mirrors again, Matthew?
These 2 mirrors are each 8 meters across.
8 meters.
So
why not make 1 16-meter instead of 2 8 meters? Someone said for depth of vision.
Okay.
Good idea. Because 1 would be too big.
Yeah.
Okay, those are good ideas. Anybody else out there? I don't know, that's all I'm getting.
Well,
I have the feeling the too big thing is on the right track, because if you get 16 meters across, that would be a lot of mirror to support.
And that's exactly right. When we're trying to figure out how to build bigger telescopes, we can't necessarily build them by building 1 mirror or 1 lens. We have to come up with these really ingenious designs where we might be using 2 mirrors. Or in a few minutes, I'm going to show you a really big telescope under construction that's going to have 7 mirrors. So this is just a start right here. But these 2 mirrors are about 8 meters across, but astronomers are able to combine the light coming from these 2 mirrors to make a telescope with an equivalent power of 12 meters across, which allows us to see even further and fainter. So basically what we're doing is we're combining the collecting area of the 2 mirrors to make an even bigger telescope. So that's why we have this telescope that has binoculars and it looks kind of like googly eyes at you, like a big owl on the top of the mountain. So we're going to just take a couple of other views of this guy. A large binocular telescope, again, sits on, see if I can get my...
While you were saying that, other ideas were trickling through while you were going through the explanation. So yeah, there were lots of folks saying that it was too big. So yes, definitely the right direction. Someone else had to concentrate the light better. To make it 3D were some other ideas.
Yeah, so thing to remember with astronomers, again, astronomers are the greediest people on the planet for light. Is that the bigger the mirror or lens, the more light you can gather, and the further away and fainter you can see. And also the bigger the mirror, the more you're able to see things like actual individual planets around other stars and figure out what's in their atmosphere. So all those are reasons why we would want to build a really big telescope and try to find ways to do it, which can include putting 2 mirrors together to make 1 like equivalent big mirror. So this is another view of this telescope. This telescope is, again, up at the top of Mount Graham in southeastern Arizona. There is this really windy mountain road that gets up to the top of it. It takes like an hour and a half to get up from a town called Safford, Arizona, down a little ways off I-10, if you're familiar with interstates and maybe that part of the country. You have to drive this windy mountain road all the way up, and then it turns into a dirt road, and then the dirt road is really windy and kind of weird, and you end up at this big telescope. So why would we build a telescope on a mountain? Seems like it'd be really hard to get up a mountain. Why do we build telescopes on really high mountain tops? So that's another question for our audience.
All right, so we're polling the audience. Why would we stick all of the telescopes on top of mountains? There are a lot on mountains in the desert and in Hawaii and in South America, all on mountaintops. What do you think some reasons are for that? See, Judy says we went to Arizona too, Hayden and Nicholas. It is a beautiful, beautiful part of the country. So yeah, do astronomers just want a really nice view during the daytime when they're supposed to be sleeping? Or why would we put these telescopes up on a mountain, do you think? Let's see. Someone says you could see more of the sky is a good idea. Okay, see more of the sky. Any other reasons for building them on these mountaintops, these remote locations that are really hard to get to, that have windy, treacherous roads? Because mountains are huge. They are huge and high. Maybe you mean high. They are very high up. So what would be an advantage of being really high up? See, someone says to see stuff better and closer is another idea. Okay. Any other, to improve it, visibility is another idea.
I think
right.
all are on the right track.
Mm-hmm.
You want to build your telescope on a mountaintop so that you are up above a lot of the atmosphere, above a lot of pollution and all that atmospheric turbulence. Remember how the moon looked like it was kind of jostling around when we looked at it a few minutes ago? So you want to get above all that atmospheric turbulence. The other thing you want to do is you want to build your telescope far away from a city. And even here on Mount Graham in Arizona, the cities of Tucson and Phoenix cause a little bit of light pollution. So this is like the closest you want to get to a big city that you ever really want to build a telescope.
And a few folks have thrown out the idea of less light pollution. Less light pollution, remote area to minimize distortion, less pollution and ground clutter, less atmosphere to look through.
Yep. The other thing is you'll notice in this picture, the sky is super blue. So we want to build telescopes, not just on any mountaintop, like we wouldn't want to go build a telescope necessarily on our mountains here in like North Carolina, because those mountains are cloudy a lot. We want to build our telescopes on mountains where the air is very dry and clear, and we get a lot of clear nights. Because what good is your telescope going to do if you build it in a place where it's cloudy all the time? We have that problem here with our telescope. So our location's great because you can come and see it and look through it really easily, and you don't have to fly across the country or down to South America and go up this really crazy road. But the trade-off for that is we're kind of in the middle of a lot of light pollution. Oh well. Just another picture, and then we're going to kind of go through other things a little bit quickly because there's some stuff I want to focus on here. But this is a close-up of the Large Binocular Telescope looking at one of the mirrors. And what's really common on a big telescope like this is they often don't look like tubes or anything like you're used to a telescope looking. They're often this big sort of superstructure kind of thing supporting the mirrors. And then the secondary mirror, so there'd be another mirror kind of up there out of the picture. And then there are various places where you can put your camera to actually look through the telescope and get the image. So now we're going to get back on a plane and we're going to fly from Arizona down to Chile.
Wow.
South America. So lately, a lot of the really big telescopes have been built or are being built down in Chile in what's called the Atacama Desert. The Atacama Desert is one of the driest places on Earth. If you're there, it kind of looks like you're on the surface of Mars. And it also has, it's away from light pollution. You're not close to any big cities. And also you get the foothills of the Andes Mountains there. So there are lots of really great mountaintops to build your telescopes. So we're going to take off now and we're going to go to a mountaintop called Las Campanas in Chile. And this mountaintop actually has two more of kind of the earlier of this generation of giant telescopes. These are called the Magellan telescopes. And you can see they're sitting here in these sort of weird looking structures. They aren't really dome shaped. And this is one of the common things we see in these giant telescopes is they don't look really like you'd think of an observatory looking, like a dome with our dome, like our dome. But these giant structures here, you can see this beautiful view of the night sky. It's a very clear sky. And to give you an idea of the size of these guys, these telescopes have 6.5 meter mirrors. So they're kind of a little bit smaller than the Large Binocular Telescope. And I don't think they're combining their light, although I could be wrong on that.
I'm not sure about this pair.
Yeah, This mountaintop is important because another telescope called the Giant Magellan Telescope is going to go in the same area. So more on that a little later. Then just a cool picture here. It's kind of neat. One of the neatest things about traveling to these observatories is actually being on the mountaintops, because really cool things can happen. So what do you notice about this picture? Here are the Magellan telescopes here on the top. These buildings right here are probably like the astronomers' dorms. That's where they would sleep and they would have their meals and such. So the staff that are up running the telescope and such, this is kind of where they live. And then there's
That's a good point. You don't have to commute up and down the mountain every single day. That would be quite a treacherous commute. You actually live up there.
Yeah, there's some more telescopes over on another part of the mountain over here. But what do you notice about this picture right here? What's kind of pretty about it?
I don't know. I see a lot of snow.
And everyone see the snow?
That's I miss snow. Anyways, I don't know what stands out to you folks out there who are watching. What stands out to you when you look at the picture of these telescopes?
Liz stole it.
What's that?
You stole it, Liz. It was the snow.
I stole it. It's the snow. It's the snow, really.
But that's actually one of the things that can happen is while these mountaintops often have very clear weather, they can sometimes make their own weather. So I used to work at a place called Kitt Peak Observatory out in Arizona. It's another mountaintop near Tucson. And I used to help run public observing programs out there. And I remember a night where we were getting ready to start our program, and all of a sudden the sky goes from clear to foggy in about 10 minutes.
Mm-hmm.
So it's like, where did that fog? What's going on here? And we actually had to send all of our guests off the mountain and cancel our program that night. And the reason we had to get them off is so the fog didn't get worse after it got dark. And we wanted to get them off the mountain safely. So yeah,
something like that happened.
Dynamic environment. All right, so Chile.
How often did
Go ahead, Liz.
Oh, sorry. My internet is freezing up on occasion, so it'll disappear. That's why. But how often did something like that happen, where fog would just suddenly roll in and just kind of mess up your plans for the evening?
It wasn't super common. It tended to kind of track towards the time of year. So like during the winter out in Arizona
Okay.
gets some winter storm type things. And often when you have one of those that have just moved through or is approaching, that's when you can get like the sudden fog that just shows up. The other thing is out in Arizona, there's what's called monsoon season. Liz actually did her graduate work in New Mexico, where there's monsoon season too. And this is the summertime, like between July and September, where you get a lot of thunderstorms. And the thunderstorms love to come and form over these mountains. Chile doesn't really get that, but Arizona definitely does. All right, just want to watch our time here. So we got a couple of other telescopes to see, and then we're going to take a tour of the University of Arizona Mirror Lab. So we're going to go now to another mountaintop in Chile. We're going to have a look at this giant thing. This telescope is called the Vera Rubin telescope. It's named after an astronomer. This telescope, unlike the Magellan telescopes and the Large Binocular Telescope, isn't finished yet. This is one of the first of these brand new telescopes that are under construction. It's probably going to be one of the first to actually start working. And it has an 8-meter mirror, so you can kind of see the mirror down there. And this mirror is in some ways similar to the 8-meter mirrors on the Large Binocular Telescope. There are some differences, but one of the big similarities is that this mirror, the Magellan telescope mirrors, and the Large Binocular Telescope mirrors were built at the same place. And that is this University of Arizona Mirror Lab under the U of A football stadium. So that's coming kind of at the end of the program. But what's really cool about this telescope is it's going to have this giant camera up here in the front. And this camera is going to, I'm going to get myself some notes here. What's going to happen is this telescope is going to, over about 10 years, look at the whole sky a whole bunch of times and take pictures of the entire sky using its giant camera. So we're talking about a telescope that can make images, each image the size of like 40 full moons. So you're looking at this giant part of the sky, and the telescope's actually going to take pictures of the entire sky every night, every couple of nights actually. So not every night, but every few nights. And then once it takes a picture of the entire sky every few nights, it's going to go take another picture of the entire sky every few nights, and then another, and another, and another, over a course of 10 years. This thing is going to generate, ready for this, 20 terabytes of data a night.
That's a lot.
That's a lot of data. Yeah, so
a lot of data to analyze, but lots of cool science will come out of that.
Yeah, so that's actually, why the heck would we want to build a telescope that's really big? It's down on a mountaintop in Chile and it has a giant camera and it looks at the sky a whole bunch of times. Why would we do that? So that could be a good sort of poll the audience question there.
Sorry, okay, what, could you state the question one more time?
Why would we want to build a telescope like this that's going to scan the sky and take a picture of the entire sky every few nights? Why do we want to do that?
Yeah, why not just one picture? Isn't that good enough?
Yeah.
We'd want to scan it
and
over and over and over again.
Over 10 years. Why don't we do it?
It's like a natural question to ask. While folks are thinking about that, so why would you want to scan the skies and take repeated pictures of it over and over and over again? I don't know if you talked about it earlier, but we're talking about mirrors, all these big telescopes with mirrors. Why not make telescopes with big lenses like the Clark? Why do we keep going to mirrors? Why are all these giant telescopes mirrors?
Let's actually hold that thought because we can talk about that when we get to the mirror lab.
Okay. All right. Let's see. All right. Any ideas out there why we would scan the skies over and over and over again and take so many pictures? That is a lot of data to have to store. So many high resolutions. Somebody said looking for something new.
Mm-hmm.
Maybe something that wasn't there before.
Very good.
All right. Any other ideas out there? Okay, not getting anything. I mean, that's kind of what I would say, looking for something new that wasn't there before.
So that's actually one of the big things that this telescope is going to allow us to do, is to look at things that might just pop up in the sky. Because stuff does pop up. You can get distant supernovae, you can get asteroids or other things in our solar system. There are these faint things that can pop up. And what this telescope is going to do is look for those constantly over a long period of time with a really huge camera and a really big mirror. And this is actually going to we're going to learn a lot from this telescope about things like dark matter, dark energy, about things that change in the sky, about things in our solar system that we might not know about, like maybe some really faint stuff, kind of like Pluto that's way out on the edge of the solar system, for example. So there are a lot of reasons to build a telescope like this. And
someone said also, this is a good one, searching for subtle differences in light, because there are things that change brightness. There are stars called variable stars, where the brightness changes, sometimes regularly, sometimes semi-regularly. So yeah, that's a good one. And someone said documenting changes, differences would show up more quickly. Yeah, that's all along the lines of what we're talking about. So yes, awesome ideas, everybody.
And one of the cool things about this telescope is, and actually there's some work on exactly how this is going to work, but it's all being worked out because, again, this thing's going to generate so much data. But the idea is to make the data from this telescope publicly accessible. So there are going to be some interesting education initiatives involving teachers and classrooms and even planetaria and science centers and such that are going to come from this. So it's going to be a really cool telescope, not only about what it's going to help scientists learn, but about what it's going to help you all as our audiences learn. So that's something that I'm kind of looking forward to about this telescope. We're going to take a couple of other views of it. One of the things I wanted to really emphasize is that these telescopes are not dreams. These telescopes are being built. So this is an artist's conception. This, oh, by the way, I forgot I put this in here. This is an artist's conception of kind of a cutaway of the building. So you can see here's the telescope right here. And then it sits on this pier. And then there's this building over here that's got lots of computers that help to run the telescope and store the data and all of that. So it's this large structure on top of the mountain. And if we go here, you can see here is this telescope under construction on a mountain in Chile. So you can see, again, this is a support building. This is where the telescope goes. These are the doors of the dome right here that are going to open to let the telescope look out in the sky. So if you've been to our observatory, you know that we have a dome that we open up so we can see the sky. Well, that's the part of the telescope enclosure that opens here. And then we're actually going to go inside here. Telescope isn't in yet, at least in this picture, but you're actually looking at the inside of the enclosure.
Maybe you want to explain why telescopes have an enclosure in the first place. Why do we even have a dome? Why not just leave it open?
Well, of course, I like to note that you don't want to get rain on your telescope. But actually, there are several reasons. Generally, we want to protect our telescopes. So we want to protect them from stray light. We also want to protect them from things like wind. These mountaintops can get really, really windy. It's not unusual to go up to these mountaintops and have 50-mile-an-hour winds. And you want to protect your telescope from all of that. And if the wind gets fast enough, you actually have to close the telescope up and not open it. That's actually true here. Here in our observatory, if the wind goes above about 40 miles an hour, we have to close the telescope down. So if there's a day when maybe we've just had a cold front go through, the wind's gusting up a lot, we have to close the dome. And that's true in these telescopes too. But if the wind is a little bit less, you still want to protect your telescope from that. So a lot goes into building these enclosures to protect the telescope. So any questions for our next stop on our tour?
There were just some comments related to things we discussed earlier, as why you would survey the sky like that. Someone suggested looking for new constellations. Constellations aren't really things you discover, though. They're just playing connect the dots with the stars in the sky and making pictures and stories to go along with them. So that's something that cultures all over the world have done throughout all of human history and what people continue to do today. But maybe looking for new objects like what Matthew was saying, supernova, or things that are there that weren't there before. And then a comment about why we would have enclosures so you can work the telescope inside. So yeah, kind of protect it from the elements and whatnot.
Cool.
All right. Where are we going next?
We're going back to Las Campanas, actually.
Okay.
We're going to a telescope that is under construction, not nearly as far along. So we talked about the Magellan telescopes earlier. Well, now we have the giant Magellan.
Woo. Again with those creative names.
Creative names. So this is a
giant one
that has, so we talked about the large binocular telescope, which has 2 8-meter mirrors. This thing's going to have 7 8-meter mirrors. And so far, 5 of those mirrors have been built or under construction. So we're building the mirrors, we're building the site. We'll show you some pictures of that in just a minute. But this telescope with its 7 8-meter mirrors, it's going to be the equivalent of like a 24.5-meter telescope.
So this is an artistic rendering.
An artistic rendering, yeah. So the Hubble Space Telescope has a 2.5-meter mirror. The James Webb Space Telescope is going to have a 6.5-meter mirror. Now we're talking about a telescope that has a 24.5-meter mirror. And a lot of people think, well, you know, we're probably not going to be building telescopes on the ground much anymore. We're going to be sending them into space. That's actually not true, because we can't send a telescope this big into space because we can't launch it. It's too heavy. The other thing is, if your space telescope breaks, then in the case of Hubble, you have to go up on the space shuttle to fix it. In the case of James Webb Space Telescope, if it breaks, it's going to be too far away from Earth to do anything about it. So if it breaks,
miles.
It's done. With these telescopes, it's just a trip up a mountain to fix a problem. So those are some of the big reasons we still build these big telescopes on the ground. And astronomers also have technology called adaptive optics, which is a whole other program in and of itself. So that might be about the future, where they can actually correct for all that atmospheric distortion and make really sharp images.
We have a question. Who is going to be running the Giant Magellan Telescope?
Giant Magellan Telescope is going to be run by a number of different institutions. I can't remember all of them, but it's like University of Texas, University of Arizona, Texas A&M. So it's like this collaboration of universities that are going to be running it all together and pooling their resources. So we're going to take another perspective. Again, this telescope hasn't been built yet, but what you're seeing is an artist's conception of the telescope right here, but it's been photoshopped into the mountain where it's going to be built in Chile. So the mountain stuff here is real, but the telescope is artist's conception. You can see here's mirror number 1, 2, 3, 4, 5, 6, and 7. They form like one giant mirror when they work together.
It's like a big desert flower there.
Oh, and then, like I said, these telescopes are under construction. So this is actually at the site of the Giant Magellan Telescope. They aren't building the telescope itself here. They're actually building something a lot more basic, a water tank.
Why do we need a water tank?
Why do we need a water tank at an observatory? Yeah. So a couple of reasons. One of the big reasons is that, well, you actually have people up here. They need water to drink, to wash dishes, to take showers. And on these mountaintops, often you don't have like regular access to water, and you actually have to load the water up on a truck and drive it up the mountain and store it in tanks. So yeah, you definitely need your water tanks.
We do have a question here. I'm just going to read it to you. See, Paula's asking, did I miss an explanation of why these telescopes are in foreign countries? Are they paid for by their governments, or is the US not interested in this phase of exploration?
Great question. So these telescopes that I'm showing you are US telescopes. They're run by US institutions, but they're being built in Chile. And they're actually agreements between the US and the Chilean government that have been in place for several decades now that have allowed this to happen. And the reason why this is happening is it's really very much scientific. It's because you, again, want to build your telescope in a place where you've got high mountains and very dry weather, dark skies, and it turns out that Chile is one of the best places for that. The other thing is Chile is also in the southern hemisphere, so we see an entirely different set of stars. So these are actually United States telescopes that are being built in Chile with agreements that are in place with the Chilean government. There also are a whole bunch of telescopes that are from European countries that have been built here. So all these various partnerships that allow astronomers to do this. Great questions, like why would we not?
That is a good question.
In the United States. And we do have Hawaii. That's another one of the big US sites. There's a telescope called the 30-meter telescope, which is kind of similar in size to Giant Magellan. The 30-meter telescope construction right now is stalled. And that's because the mountaintop called Mauna Kea in Hawaii is a sacred mountain for the native Hawaiians. And there's a huge disagreement going on right now about building this telescope. And it's going to be real interesting to see if it actually happens. But there have been, like, for a year before COVID, back in, like, I think 2019, for several months, there were these protesters on the road up Mauna Kea, keeping the construction vehicles from going up the mountain. So that particular, it's one of the big concerns in astronomy right now, is one of our best United States sites on US soil has got this really big problem with its local population having real disagreements about whether these telescopes should even be built. And there are arguments for and against it, honestly. That's actually another whole program. We're going to get on a plane again.
Where are we going now?
We're going back to Tucson.
Okay.
There's a real connection again between Arizona, where we have these US telescopes like the Large Binocular Telescope, like Kitt Peak, and these giant telescopes down in Chile. And that is at the University of Arizona. In this mirror lab is where we make the mirrors for them. So we're going to go have a look here. So this is the University of Arizona Mirror Lab. It's this funny building that sits under the football stadium. So why do you think we build a mirror lab under a football stadium? Any ideas?
Interesting question. So for those of you watching, what are your ideas about why we would build a mirror lab, or basically a place to construct these giant mirrors for these really awesome telescopes? Why would we put that under a football stadium? Of all places, why is that a good location, do you think? Oh, let's see. Why would we build mirrors under a football stadium? Well, I don't know. I'm not seeing anything yet.
We actually have...
It's large. It's a large space, but you can get large spaces elsewhere.
You also have these pillars that are there supporting the football stadium that you can also use to help support your building. So that's one. Well, let's actually go inside this mirror lab and see what's inside. I'm going to tell you, having been in this multiple times and been on a bunch of tours of it, these pictures do not do it justice. When you're inside this lab, it is impressive. So we're going to go inside here. And let's see if I can get my screen to advance. And we're going to learn about how we make these mirrors.
Ooh.
Mirrors are really special. They're what are called honeycomb mirrors. And right here, they're actually making the honeycomb form for one of the giant Magellan telescope mirrors. So you got these honeycomb things. And the idea is that the glass, when you melt the glass, it goes down into this honeycomb structure. And that helps support the mirror. And it allows you to make a mirror that's largely hollow, but extremely, extremely stable and stiff. And because the mirror is hollow, it's lighter. When your mirror is lighter, you can make a bigger mirror. You don't need as big a telescope structure to support it. And it just makes the whole thing a lot more doable in terms of engineering. So one of the things we asked about is, why not make a really big lens? So it's really hard to make a big lens. Big mirrors, the light doesn't have to travel through the mirror, it just reflects off the surface of the mirror. A big lens, the light actually has to go through the lens. And if you're trying to make a lens this big, like a 8.5 meter or an 8 meter lens, your lens is going to be so thick and massive that the telescope structure to support it, you just basically couldn't build it. It'd be too heavy and too expensive. And also, as you move your telescope around, looking at different parts of the sky, the lens, because it's so heavy, it's going to bend and distort your images. But what's happening is this honeycomb structure for this mirror is being built inside this furnace. So this big circular thing is this giant furnace. And the furnace heats up the glass. So we're going to show you a close-up of the glass being installed. So these pieces of glass right here that are built at a company in Japan. And if I remember correctly, a lot of the sand for the glass comes from Florida. So you take your sand from Florida, ship it to Japan, make your glass, and then send it back to Arizona. And it's a very special type of glass we have to use.
Yeah, I wonder what makes that Florida sand so special.
I don't remember. I used to know. But the glass comes in these chunks, and you can see this engineer here is putting the glass chunks into the furnace and lining it all up in that honeycomb structure. So now, ready for the next picture?
Yeah, we do have one question. Is this lab actually under the stadium, or is that whole building the lab? It is underneath.
It's not like underground, but it is under the stadium. Mm-hmm. It's above ground, but under the stadium structure. So we've zoomed out. We're taking a look now at this giant furnace. And this is the lid of the furnace. And there's a big crane that has this lid. And the lid is going to get lowered down on the furnace. So now the lid's in place. And now once we have the lid in place, we can start the furnace up. So over a period of time, the furnace is going to heat up to about 2,100 degrees to melt the glass. And not only is it going to be heating the glass up, it's also going to spin. So this is a spinning furnace. Now this actually makes this picture makes the furnace look like it's spinning a lot faster than
It does. It looks like it's whizzing around at a really high velocity.
But it's spinning only about 5 times a minute. So that's actually plenty fast for something this big, but it's not like whizzing around like you're on some kind of, ride at an amusement park. So, but why would we spin the mirror while we're casting it, while we're making it in the furnace? Why would we spin it? What are our thoughts from the audience?
Is that okay? So that's a question for our viewers. So why would we put a bunch of glass in this giant furnace and then spin it around while baking it at a couple thousand degrees? So any ideas out there about why we would spin the glass in this giant furnace? Let's see. Oh, well, lots of wows. It is really impressive.
This is a good response here.
Now, while people are thinking about that, are there any other mirror labs like this in the country? Or is this the one or the main one?
Only one like it in the entire world.
Wow.
Yeah.
Pretty special. See, Paula says centrifugal force to help spread out the melted glass thinner.
Ooh, that's so close.
Oh.
Is that
oh, to create friction?
What you're
another idea
is you're actually getting the glass to curve. Telescope mirrors are not flat like the mirror in your bathroom. They're actually curved. So the upper parts are lower than the part in the middle. So it's a curved thing. On old telescope mirrors, and actually we still build smaller mirrors like this, but on smaller telescope mirrors, you'd start with this flat piece of glass, and then you'd have to actually grind the glass out to get that curved shape that you need. And that curved shape has to be accurate to smaller than a human hair to reflect the glass properly, reflect light properly. But if we spin the mirror, we can actually start getting this curved structure in even while we're making the mirror blank, even while we're just starting the mirror. And that actually saves a lot of time and expense when we polish it. So the glass is heated up and spun around, and then it slowly cooled down, and the furnace slowly slows down. Then you end up with what's called a mirror blank. And this mirror blank right here that's being hoisted, and this is kind of scary because you have this giant chunk of glass that you're now trying to shake over to another part of the lab. So it's like, don't drop anything.
Don't drop it.
Drop it. So it actually goes over to across the way, and it goes to this polishing lab right here. And this polishing lab, you can see this is one of the giant Magellan telescope mirrors right here. And then this right here is the grinding instrument or the polishing instrument. And you can see how it's loaded up with all of this stuff. And this polishing instrument is driven by computers, and it actually can change its shape very, very quickly to get the shape that you want for the mirror. So one of the things you might notice is that this mirror doesn't look like a mirror. It doesn't look reflective, does it?
No, it just looks very see-through, just like the bottom of a colander or something.
Yeah. So what actually has to happen is when you get the mirror to the telescope, the mirror has to be covered in this thin layer of aluminum. And the mirror is put in this giant vacuum chamber, and these are again at the telescope for these big telescopes. You don't want to be transporting your mirror off a mountain to do this. So the mirror is coated with aluminum. That makes it reflective, but the layer of aluminum is only a few atoms thick. It can fit in a Coke can. So
it's not a lot of aluminum.
giant hunk of glass that takes you 4 years to build just to support a thin layer of aluminum. Now, is that like weird? Yeah. Okay, a couple of other pictures. We are getting close to the end of our time.
We are.
But what happens now with these mirrors is that they're loaded up on giant trucks. This is one of the giant Magellan telescope mirrors, and it's actually on this truck, and it's being taken to this hangar at the Tucson airport. And this is actually where it's in storage. And then once the telescope in Chile is ready, this mirror is going to be trucked off to a port, probably like the port of Long Beach would be my guess, out on the west coast near Los Angeles. And then it's going to be loaded on a ship and taken by ship down to Chile. And then once it gets to Chile, it's taken off the ship, and then it's driven up to the telescope up the mountain on another big truck. So we don't have a picture of that yet, because remember, these mirrors aren't down to Chile yet, but we're going to go back to the large binocular telescope that we started with. This is kind of a blurry picture, but this is a picture of the large binocular telescope mirror, or one of the mirrors, being driven up Mount Graham. So here's your truck, here's your mirror, and the truck is going up this really narrow dirt road, and that road switchbacks like this. And actually are times when the truck would overhang the road with its wheels. 8-meter mirror, and it's like,
yeah, you talked about don't drop it when it's in the lab. Don't drop it down the side of a mountain. That would be.
Before it had to drive from Tucson on Interstate 10 all across for probably about, I think it's like 80 miles or so, if I remember right. I've driven it before.
Spent all that time making it, and now it has to survive several treacherous trips. This is very nerve-wracking, I imagine.
You're driving it down the interstate with this police convoy. It's a huge operation getting these telescope mirrors on mountains. All right.
All right. Well, we are almost out of time. So what are we going to do in these last minutes? Are we going to go back to the moon at all?
We are going to go back to the moon. I do have a quick video I can show you, and I'm going to just show this really, really fast because I want you to see what the mirrors or the furnace actually looks like when it's rotating. So I'm going to set this up real quick, and then we're going to go and have a look. Give me just a second.
All right. If anybody has any questions, last minute questions here while we start to wrap things up, go ahead and put those in the chat.
Let's see if we can find the part where the furnace is spinning. I'm just going to go through here. I'm talking about the glass there.
Foot diameter oven is then gradually heated to a temperature of 1,350 degrees Fahrenheit over the course of a week. There are cameras in the oven to monitor.
That's actually a camera looking at the inside of the oven as the glass melts.
Oh, neat that they did that.
Begins, there's no turning back. At this point, the massive oven is filled with 19 tons of glass and starts to spin 5 revolutions per minute. Once the oven reaches 2,129 degrees Fahrenheit, or 1,165 degrees Celsius, the consistency of the glass is about the same as honey and starts.
So there's the furnace rotating. It's really quite.
Ooh.
Well,
yeah.
In our
super
time,
cool.
We're going to come back, going to get on a plane. We're going to fly back to Columbia here to our observatory, our wonderful observatory that you can come visit, and especially once this whole COVID madness winds down. And we're going to have another look at the moon. Now, I might have to get the dome rotated or something like that. Yeah, I'm going to need to rotate the dome. So I'm going to go ahead and get screen share started. And then I'm going to rotate the dome and get ourselves a view of the moon. So here we go. Give me just
right. So we went to deserts or throughout the US and around the world, and then we're going to go from there back to the moon. So taking a trip to lots of different places this evening. And if you joined in at the beginning of the live stream, we took a close-up view of the moon. And that's what Matthew has gone off to go into the dome, rotate the dome around, and make sure the telescope is pointed through that little window there that we have on the sky. And there it is. So if you haven't had a chance to go outside and look at the moon, it is very beautiful and clear right here in the Columbia area. The moon is just past first quarter, so it's just a little more than half lit up. And here we are looking at some craters.
Drive the telescope around just a little bit so we can see another part of the moon. Up, up, up.
I love driving around on the moon.
Right.
And Paula says trips without vertigo win for sure.
We try to do this without inducing vertigo. Let's see if I can get to it. I want to try to get a good direction here. Get down to maybe
Okay.
It's got a little more sunlight and it's brighter.
Okay, going. And as Matthew described earlier, we were looking there along the terminator, which is the dividing line between the day side of the moon and the night side of the moon. And we're kind of going a little more towards the day side here.
Yes, now we're really on the day side.
I think I see some features I might recognize on there. Oh, well.
All right.
We've got those smooth, dark areas, those ancient lava flows, lots of craters.
Well, what a trip we've taken tonight.
We have. We went to the moon, we went to deserts, and then back to the moon.
Yeah, so
right.
Lots of fun here. These telescopes are these big telescopes we talked about tonight, they're going to be coming online and start working, if everything goes as planned, this decade, so in the 2020s. So kids out there are wondering if you become an astronomer, these might be some of the telescopes you use.
Lots of cool telescopes. So yeah, we wanted to give you some perspective on other telescopes, not just the ones that we have at the observatory, but there are lots of different types of telescopes, ground-based telescopes and space-based telescopes, which I hope we'll get a chance to talk about in a future program. All right, well,
I think
we are out of time. So I guess we'll just thank you everybody so much for joining us. Thank you for your wonderful questions. Thank you so much for participating and being part of the conversation. Go out, enjoy the moon if it's clear. It is beautiful tonight. Go out, do some stargazing. And don't forget, we do these live streams on Saturday. The time will start to shift backwards up in the future as sunset gets later and later. So just be sure to check our Facebook page, check our website to make sure that you got the time right.
Yeah, that's a point. Starting February 6th, so the first Saturday in February, we're going to move the time later to 7:30 to 8:30 because the sun is starting to set later.
The sun. All right.
Hi.
All right, any final thoughts? So thank you, everybody. Matthew, anything you want to say?
I think it's been a really great trip. I hope you enjoyed it as much as I did.
Yeah, all right. Well, thank you, everyone. Bye-bye, and hope to see you here next week. All right, take care out there.
Be safe and healthy, everyone. Bye.
Bye-bye.